Hi, everybody. This is Dr. Nigro with the Chem Calculation Screencast. The screencast is going to look at Gibbs Free Energy within equilibrium systems, so systems where the reaction is reversible. It can be a little confusing. It's pretty formula driven, so if you can understand how to look at the formulas to determine the relationship between the favorability and the equilibrium constant, you're going to be all set. But I do want to preface this by saying that in general, it can be a little confusing in terms of how you get from Gibbs free energy to that equilibrium system, but we can do it. All right, so let's start with our understanding that delta G tells us the favorability of a reaction or process. All right, so we know that delta G is a measure of the free energy that is available after a process or reaction has occurred. And if it is a negative value, that means that free energy is released. So there was excess free energy. Whereas if delta G is positive, then that means the universe had to supply that energy. So processes that put energy out into the universe are going to be favorable, whereas processes that require energy from the universe are going to be unfavorable. All right. As a reminder for that and how to calculate delta G, please go back and look at that screencast that dealt with delta G and entropy. All right. Now, I want to add a piece here. I'm going to put this 0 here. And this tells us that we are under standard conditions. All right. And we should define that as we move forward. All right. Similar to our gas laws, it's 1 atmosphere of pressure for any gas involved, 25 degrees Celsius or 298 Kelvin. And now, because a lot of our systems are going to deal with solutions, those solutions should be 1 molar in concentration. So all those tables of information that we use to calculate delta H, delta S, or delta G, they're all going to be standard condition data, which is great, except that not every experiment that we run in a lab is under standard conditions. So we need to calculate the free energy for a system under non-standard conditions. So non-standard conditions. Our delta G naught becomes delta G without the 0. All right, now to calculate this, we need to know the standard condition value, and then we are going to correct it based on the temperature and the concentrations. So we're going to use R times the temperature times the natural log of our reaction quotient. Remember, that's products over reactants, and we use our coefficients as subscripts to calculate that Q value. All right, now you can see our friend, the gas law constant here, R. All right, it's going to be a little different for this setup because we're dealing with energy values versus gases. All right, so we're going to use 8.314 for that numerical value, and our unit will be joules per mole Kelvin. All right, so remember, Kelvin is going to dictate our temperature, so that temperature needs to be in Kelvin. And joule, we may need to adjust because our delta G naught might be in kilojoules. So just pay attention to those units. All right. Now, this is what our system looks like under non-standard conditions when we are not at equilibrium. All right. But what if we are at equilibrium? All right. In that case, this free energy value becomes 0, and we need to swap out Q for K. All right. So that's going to adjust our formula. We're going to have 0 equals our standard entropy value plus R times T times the natural log now of K. And we can solve this for delta G under standard conditions. So another way to calculate delta G under standard conditions is equal to the negative value of R times T times the natural log of K. All right, this formula is very important because it allows us to relate the free energy of a reaction or process to its equilibrium constant. All right, so if you think about an equilibrium system, right, we've got A, goes to B, and B goes to A. So this would be our forward, and this would be our reverse reaction. All right, well, our enthalpy change for that forward reaction is going to be equal but opposite, not enthalpy, free energy change of our reverse reaction. So if your forward reaction is favorable, then the reverse reaction is unfavorable. If the forward reaction is unfavorable, then the reverse reaction is going to be favorable. All right. So when you have an equilibrium system or a reversible reaction, then there is a relationship between the free energy values, but it is an equal but opposite one. You cannot have both reactions be favorable or both reactions be unfavorable. One will be favorable over the other. All right. So now we need to think about the different ways to calculate delta G. We have our delta G relationship with the equilibrium constant. We also can relate it to enthalpy and entropy changes, and we can calculate it if we have the standard values for our reactants and our products, and we can subtract those from one another. All right, so any of those three are going to allow us to calculate that free energy change. And we can mix and match these formulas now. Let's say we know the equilibrium constant and the enthalpy change. We can now figure out the entropy change. Let's say we know the enthalpy and entropy change. We can figure out the equilibrium constant. All right, so it's really convenient to be able to mix and match these delta G formulas. All right, so let's talk a little bit about this relationship between the equilibrium constant and our favorability. All right, so for favorability, whoops, we know that our delta G value, where'd you go, buddy? Oh, sorry, hold on, let me do this again. For favorability, we know that delta G needs to be negative. All right, so let's think about what that means in terms of our equilibrium constant in that formula. All right, so let's say we have a process where our equilibrium constant is greater than 1. So that means that we have more products present at equilibrium than we do reactants. All right, so if we take something larger than 1 and plug it into that formula, then the natural log of that value is positive. And according to the formula, that'll give us a delta G value that is negative. And when I say formula, I'm talking about this one right here. All right. So if this K value is greater than 1, the natural log of that number will be positive. And when that negative sign is taken into an account in that formula, we're going to get a negative delta G value. So when you have products over reactants and you have more products present than reactants, that forward reaction has a negative delta G value. So it is the favorable reaction. If instead your equilibrium constant is less than 1, then the natural log of K is going to be negative and your delta G value will be positive. All right, so if you have more reactants present at equilibrium than products, then that forward reaction is unfavorable and the reverse reaction will be favorable. All right, and then finally, if you have equal amounts of products and reactants, then your natural log of K is 0, which is going to give you a delta G value of 0. So in this case, neither reaction is favorable. They are both equal to each other. All right. All right. So understanding that relationship between delta G and K is also going to be important because the ratio of products to reactants gives us an idea of which reaction is favorable, the one towards products or the one towards reactants. All right. Now, we know that favorability is dependent on the value and sign of delta G. All right, but it can change. We saw that with our formula for enthalpy and entropy, where it was dependent on temperature. All right, but there are other ways that we can influence the favorability. And one of them is by adjusting the concentration of our products and the concentration of our reactants. All right, we know that when we adjust the concentration of products and reactants, Le Chatelier's comes into play, and that influences the direction of the reaction, which in turn will influence the favorability of the direction of the reaction. All right, so we adjust the concentration of products and reactants, changing Q. All right. And then we can use our formula again to determine what is going to happen. All right. So let's look at this graph. So first up, I want to point this out. This is standard conditions. All right. For this particular one, the reactants have a higher free energy than the products. So when you do that subtraction, you're going to get a negative value, which means that free energy is being released out into the system. All right. At equilibrium, all right, right here. All right, this is when k is greater than 1. So we're going to get a natural log that gives us a positive value, which is going to give us a negative delta G value, which matches what we see with just our reactants versus products. All right, so when we're down at the bottom of this, we have a mixture of products and reactants. And because we are closer to the product side, that's where our K value will be greater than 1. All right, but what if we adjust those values? So let's say we're looking at a point where we have a reactant to product ratio that would be here. So this is Q. And in this case, we're closer to the reactants than the products. All right. So in this case, Q is going to be less than 1. All right, so the natural log of Q is going to be negative. All right, and that adds to our delta G naught. All right, so what that means is your delta G is going to become more negative. So it's moving down that hill towards those products. So it's more favorable to go towards those products. All right, what if instead we were over here? I know you can't really see the line there, but you'll know what I mean. So again, this is going to be Q, all right? But in this case, we have more products than reactants. So we've passed equilibrium and we've headed up that hill. All right, so the natural log of Q here will be positive. So we're going to take away from delta G. So in other words, we're going to make it less negative. So it becomes less favorable to move forward. All right, so instead, the reverse reaction becomes a little bit more favored. All right, so that's what Q can do for us. But for that, you got to keep in mind the formula, right? So just use your delta G equals delta G naught plus RT, natural log of Q, to determine how that change in concentration is going to influence the direction of your reaction in terms of its favorability. Okay. All right, so let's work a couple problems. All right, like I said, a lot of this is formula driven and then just explaining how your answers are reasonable. So reasonability is going to be important here because you can compare your G, delta G and your K values, and they should match up in terms of favorability and what is present at equilibrium. All right, so in the reaction, P2 is converted into pH3, so at P2 plus 3H2, reversibly forming pH3. At 298 Kelvin, what is the equilibrium constant for the reaction given that delta G for P2 is this, delta G for H2 is this, and delta G for pH3 is this? All right, so we're asked to figure out the equilibrium constant. All right, so I know that I need to find delta G for the reaction. So I've been given delta G values for everything. So I'm going to use delta G for the reaction equals the sum of the delta G values of formation for my products minus the sum of the delta G values of formation for my reactants. All right. Product side, we have 2 times pH3, which is 13.4 kilojoules per mole, minus, on this side, we have 1 P2 molecule, so that's 103.7 kilojoules per mole, minus, or sorry, plus, and then we've got H2 elemental form, so there's no free energy there, so it's 0. All right, so we get a negative 76.9 kilojoules per mole for our free energy value for the reaction. All right, so as you can see, we have a negative delta G value. So that means that the forward reaction is favorable. All right, well, let's see if our K value holds up. So delta G is going to be equal to negative R times T times the natural log of K. All right, now I know that R has a unit of a joule in it. You can kind of decide which way you want to go, kilojoules to joules or joules to kilojoules. I'm just going to go kilojoules to joules. So that becomes negative 76900 joules per mole equals negative 8.314 joules moles Kelvin. Our temperature here is 298 K, and then we'll have the natural log of K as our unknown. All right, so we plug everything in and we get the natural log of K is equal to 31.0 joules per mole. And we take the inverse natural log. We find that the K value here is 3.01 times 10 to the 13th. Wow, lots of products. All right, so is that reasonable? Well, delta G is negative. So that means the forward reaction is favored, and the forward reaction produces products. So that is a reasonable answer. All right, so you can use those answers as a way to determine whether you have done your math correctly, which can be very handy. All right, next, benzene has an enthalpy of vaporization equal to 30.8 kilojoules per mole and boils at 80.1 degrees Celsius. What is its entropy of vaporization at this temperature? All right, so let's talk a little about the idea of vaporization. And this is going to hold for any phase change, all right? It's a process where our liquid converts into a gas, all right? That temperature, which we know is the boiling point, means the system is at equilibrium. Oh, not example, equilibrium. All right, so in this case, the free energy of vaporization for the system is going to be equal to 0. All right, so if we think about that, we can use our delta G, delta H minus T delta S. We know that delta G is 0. The enthalpy of vaporization is 30.8 kilojoules per mole. And we have a temperature of 80.1 degrees Celsius. If you convert that to Kelvin, 353.1 Kelvin. And our only unknown here is going to be our entropy change. All right, so we put all of our stuff in and we calculate delta S and we get a positive 0.0872 kilojoules per mole Kelvin, which probably should be written in joules, 87.2 joules, moles Kelvin. So this is our entropy change. All right, now, is that reasonable? Well, we know the enthalpy change is positive. It's an endothermic process. Energy is required to convert from a liquid to a gas. But we go from the liquid state to the gaseous state, we are increasing the disorder. So we should see a positive entropy change, which we do. All right, next, calculate Kp for the reversible reaction of H2 gas with N2 gas to give NH3 gas at 25 degrees Celsius. The free energy change for this reaction is negative 32.7 kilojoules per mole of nitrogen. All right, so we're going to be using our free energy and its relationship, the equilibrium constant, to solve for Kp. All right, so delta G is negative 37.2, but don't forget the units for R. So I'm going to convert that to 32700. So now I'm in joules per mole Kelvin equal to negative 8.314 joules per mole. Oh, sorry, there's no Kelvin for delta G. Kelvin, I was getting ahead of myself. All right, temperature is 25 degrees Celsius, which is 298 Kelvin. And then we'll have the natural log of Kp. as our final part. All right, so we do the math. We have a natural log of Kp that's going to be equal to 13.2. We take the inverse natural log of both sides, and we find that our equilibrium constant is 5.40 times 10 to the negative fifth. All right, so this, we've got reactants greater, oh, not negative fifth, positive fifth, which makes more sense. The products are greater than the reactants. Why does that make sense? Because delta G here is negative. All right, so delta G being negative means that forward reaction is favored. So we should see more products than reactants at equilibrium. All right, using the KSP of silver chloride at 25 degrees Celsius, calculate delta G. All right, now I want to take a moment. These equilibrium values that we have in this formula can be of any type of equilibrium constant. All right, they can be Kp, they could be Ksp, they could be Ka, they could be Kb, they could be Kc, it could be any equilibrium constant. It does not matter. It is the equilibrium constant of a particular process, and we can utilize it. All right, so let's talk about what we would expect for delta G based on what we've been given. Here, our KSP value is much, much smaller than 1. So that means our products are much, much smaller than the reactants. So I would expect delta G to be positive, meaning that the forward reaction, reactants to products, is unfavorable, and the reverse reactions, products to reactants, is favored. All right, so let's see if that holds. All right, so we again know that delta G is going to be equal to negative R times T times the natural log of KSP. All right, so delta G is going to be equal to negative 8.314. And again, joules, moles, Kelvin. All right, at 25 degrees Celsius, so 298 Kelvin. And then the natural log of 1.6 times 10 to the negative 10th. All right, so if we plug all of that in and solve, we are going to get a delta G value of positive 5.60 times 10 to the not negative, 10 to the fourth. Okay, so that delta G value is large and positive, which means that that reverse reaction is the favored reaction. All right, this is very reasonable based on that equilibrium constant showing that many, many more reactants are present than products. All right, so let's wrap it up. Calculate delta G for the reaction of nitric oxide with oxygen to give nitrogen dioxide under these conditions. Temperature is 50 degrees, partial pressure of NO is this, partial pressure of O2, partial pressure of NO2. The value of delta G for this reaction is negative 72.5 kilojoules per mole of O2. What are reactants or products favored? All right, so what we have here is an system under non-standard conditions. All right, so we're going to be calculating delta G based on that non-standard set of conditions. That formula is delta G equals delta G under standard conditions plus R times T times the natural log of Q. All right, so we're going to need to figure out what Q is, which in turn means we need a balanced chemical reaction. So I've got nitrogen monoxide plus O2 gas forming nitrogen dioxide, NO2 gas. All right, for balancing, I'm going to need 2 of these. I'll need 2 of these, and that's going to give me my balanced reaction. So I'm going to take a moment over here and calculate Q. So it's going to be the partial pressure of NO2 squared divided by the partial pressure of NO squared times the partial pressure of O2. All right, so I've got 1 times 10 to the negative fourth squared divided by 0.0100 squared times 0.200. All right, plug everything in. I'm going to get 5.0 times 10 to the negative fourth. All right, so under these conditions, the reactants are greater than the products. All right, so we're probably, if we look at our value for delta G, which is negative, all right, that means that at equilibrium, that forward reaction is what is favored. All right, so we're probably on our way there. All right, so we're heading down the hill towards equilibrium, if you want to think of it that way. All right, so we come back to our other formula and we're going to plug in our values. Again, remember R is in joules. All right, so I'm going to convert that negative 72.5 kilojoules to negative 72500 joules per mole. And that will be plus 8.314. I'm going to drop my units just because I don't have a lot of room. 50 degrees Celsius is equal to what in terms of temperature? I realize I did this wrong. That's okay. 273 plus 50 is 300. Ah, whoa, sorry about that. 323 Kelvin. And that's going to be times the natural log of Q, which is 5.0 times 10 to the negative fourth. All right, so let's see what we get here. We have negative 72500 joules per mole. And on this side, we have the natural log of 5 to the negative fourth times 323 times 8.314. So we get negative 20411, and this is in joules per mole. All right, we put those two together and we get negative 929.12 joules per mole, or negative 929.12 kilojoules per mole. All right, as you can see, this value is greater than delta G under standard conditions, the delta G at equilibrium. So we are heading down the hill towards that equilibrium mixture. So we have a higher favorability at this point in the reaction. If we overshoot that, so let's say we have more products than we're supposed to, all right, then we would see that decrease in delta G as we go down the hill towards that equilibrium mixture, but from the other direction, from the the reverse reaction side. All right, so you can see a lot of this work is just manipulation of formulas, but make sure that when you're finished, you look at your answer and you ask yourself if it is reasonable in terms of what you understand about the equilibrium constant and the free energy for that system, right? They should be in unison in that if you have a high K value, you should have a very negative delta G value. If you have a low K value, then you should have a positive delta G value. All right, because those two go hand in hand. The more products you have at equilibrium, the more favorable that forward reaction is going to be, and then vice versa. Okay, and don't forget this formula for delta G that includes Q. All right, that is super handy.